Okay, in this video we're finally going to get around to doing some hypothesis tests. We've set it up because now we know what a deviation is, a z-score, we know the overall idea of a hypothesis test. So let's dive in and actually do some hypothesis tests. Now, where you always start with hypothesis tests in any class is by doing some of these hypothesis tests involving means and proportions. And we're going to start with the proportions test. We ask ourselves, as we mentioned in the previous video, how close should a sample be to whatever the truth is? So we assume that the null hypothesis is right. Suppose I take a sample of 10 or 100 or 1,000 pieces of data. How close should that sample be to the truth? And that how close the sample should be to the truth we call the standard error. Now, some people who know statistics well might pick at that interpretation of what a standard error is, so let me be a little more specific. A standard error I think about as a common sized distance between a sample and the truth. So let me actually type that down so we can think about what that means. Standard means common, remember. It's a common distance between a sample estimate and the truth. The real mean, the real proportion, or the real whatever it is that we're looking at. And why would we call this a standard error? Well, because it is an error, if you think about it. It is an error if your sample calculation, your sample average, or your sample proportion of people who have a degree, or whatever it is you're studying, if that sample estimate is not equal to the real value of the population, then in some way there's been an error made, and we call that error sampling error. The error that's been made is because you're only taking a fraction of the population and not checking the entire population. But that's just not practical or possible in most cases. So this standard error is a common sized sampling error. It's a common distance that we expect there to be between a sample estimate and the truth. And so if your estimate is this distance away from the truth, nothing shocking, nothing interesting. But if you're 2 or 3 of these away from what you thought the truth was, you start to doubt what's going on. Something strange is happening here. How do you calculate this standard error? Well, there are very complicated, fancy formulas for some cases that you see in some classes, but the basic idea, if you're studying a sample mean or a sample proportion, the basic formula is the standard deviation of the data divided by the square root of n. The standard deviation of the population divided by the square root of n. So it does have to do with how big your sample size is. All we have to know to get going now is, since we're going to talk about some proportions questions, what is the standard deviation for a proportion? And that's pretty easy. It's the square root of p times 1 minus p. Is square root of what you think the proportion is, the true proportion, times 1 minus what you think the true proportion is, and take the square root of that. What we're going to study is coin flips, and so the null hypothesis we're going to be studying is this one that we talked about before. We think for most coins it's reasonable to start with the assumption that the true proportion of times you will get a heads is 0.5. So let's look at coin flips. If a coin really has a 50% chance of being heads, then we understand very well what the distribution of samples of coin flips, if you flip a coin 10 times, 20 times, 100 times, 1,000,000 times, we know what the distribution of your flips should look like. Not your actual result, but the distribution. What that means is we can tell the probability of getting different kinds of results. So as long as we flip the coin more than about 10 times. Otherwise, we can't use the normal distribution that we're going to use. But as long as we flip a coin more than 10 times, we can use the normal distribution. Why? Because of something called the central limit theorem that says the larger our sample is, the closer our sample estimates of means and proportions will be to having this nice bell-shaped distribution. So suppose we flip a coin 25 times. What will the distribution be for different samples of 25 flips? So if I had 100 people and they all flipped a coin 25 times each and recorded how many heads and how many tails there were, and then we made a histogram, here is what should happen. Let's calculate the standard error. Now remember, this standard error tells us a common distance between each sample estimate and the truth. What's a common distance that we should see? And the standard error is a standard deviation divided by the square root of n. And for proportions, this is how we calculate a standard deviation. P times 1 minus p square root. Basically, here's going to be our standard error. It's going to be the square root, and I'll just type SQRT so I don't have to go through the formula editor and everything. The square root of 0.5, that's p, times 1 minus p, which is 0.5. Right? So here's how we're going to calculate the standard deviation. Let's just do this in two parts. The standard deviation of the coin flips is going to be 0.5 times 1 minus 0.5, which is also 0.5, and then the square root of that. So let's see what we get. Of course, the square root of 0.5 times 1 minus 0.5 equals 0.5, right? So that's the standard deviation, a common distance away from the average for coin flips. Now, in order to calculate the standard error, how far is it going to be? What's a common distance between the sample results and the truth? We take that 0.5 standard deviation and divide it by the square root of the sample size. And I said in this paragraph, let's assume we're going to flip the coin 25 times. So the square root of 25, and so our standard error is going to be 0.5 divided by 5, which is going to be 0.1. So 0.1. What does that mean? Well, that means that most of the time, this is a common distance, most of the time our samples should be within 0.1 of the truth. And what we're saying, we think the truth is that this is a fair coin. Half the time we should get heads, right? That's what that standard error is telling us. Most of the time we should be within about 0.1 of 50%, or 0.5 being 50%. Now let's actually do a couple of hypothesis tests using this information. Here are 3 people who are kind of famous for having sat down and flipped a coin many, many times personally. And let's start with A. The French naturalist Count Buffon tossed a coin 4,040 times. It was the same coin, and he recorded each result, heads or tails, and the results were he got 2,048 heads. So let's actually do a hypothesis test of this hypothesis. Can we stick with the idea that the coin he was flipping was a fair coin? We don't know what kind of coin it was. He did this back in the 1700s. So should we stick with the idea that that coin had a 50% probability of heads, 50% tails, or should we reject it? Here are the mechanics of how to do it. What we're going to do is we're going to calculate a z-score. Z equals, and what we're going to do on the top of this formula, this z-score, is calculate how far is our sample proportion, the proportion in our sample, away from what we think the truth is, which we think the truth is 0.5 here. Then we're going to divide that by a standard error. And we're going to have to calculate that as well. So let's go ahead and do this. What is the sample proportion in this case if Count Buffon flipped a coin 4,040 times and had 2,048 heads? Well, the sample proportion, what we call a p-bar, is going to be equal to 2,048, so let me just do that on my calculator here, divided by 4,040. And you do the calculations along with me, otherwise you're not going to really understand what's happening. This is not a spectator sport. The p-bar is 0.5069. We'll round that off to 7 just for the sake of simplicity here. So that's our p-bar, our sample proportion. We're going to subtract 0.5 from that and then divide it by the standard error. We need to calculate the standard error. Why can't we use this one, 0.1, that we calculated up there? Because that was assuming 25 flips was our sample. Here we have a sample of 4,040, so we need to calculate that standard error again. So the standard error is going to be equal to 0.5 divided by the square root of 4,040. So pause the video, do that, and then see what you get. Okay, I got 0.00787 if we round off. 0.00787 is the standard error. What that tells us is that our answer, our samples that we get from a sample size of 4,040, the proportion of times we get heads should be somewhere within about 0.00787 from 0.5. That's how close we should be most of the time. Let's calculate this z-score to tell us how many standard errors we are away here. So Count Buffon's sample, 0.507 minus 0.5, that's our kind of our deviation. How far is he away from what we think the truth is? And divide that by this standard error. It's kind of like a standard deviation. In fact, it is a standard deviation. 0.00787 equals, and the z-score we get here, 0.007 divided by 0.00787, is about 0.889. That's our z-score, or our z-statistic for this hypothesis test. What should we do at this point? Here's the critical question. Should we stick with this idea that this coin really does have a 50% chance of giving you a heads, or should we reject it? And what should our decision be made on? Go back to the idea of the empirical rule for standard deviations, and for it works for standard errors as well. Let's go back up here. Remember that about 68% of the time data should be within one standard deviation of average. In this case, our average is the 0.5, and our standard deviation is what we call a standard error. So what happened here? Well, our sample was within one standard deviation. It was actually 0.889 standard errors, standard deviations, same idea, away from the average. Is that shocking if you're within one common deviation? Is that something to be surprised about or worried about? No, that's normal. That's absolutely common. That's why we call it a standard error or a standard deviation. And so we should not reject just based on that if you understand these concepts. Now, here's what we usually do though. What we want to do is calculate, okay, our result, our deviation was about 0.889 of a standard error, of a standard deviation away from the null hypothesis. We want to calculate how common or uncommon that is. And let me draw you a picture and we'll actually calculate this. Alright, here we have a drawing of a normal distribution, and these samples of coin flips that you get will have a normal distribution, as we previously mentioned, and they'll have a bell-shaped distribution. At the center is what we think the truth is, 0.5, and the common distance things are away from the truth. In other words, how spread out this normal distribution is determined by this standard error, 0.00787. If you look at a normal distribution, one standard deviation away from the center, you can tell is where an inflection point is. It's where here you can see that the bell gets steeper and steeper. However, at the top, it's getting flatter and flatter to where it gets totally flat. The inflection point is that place here where it stops getting steeper and starts getting flatter. And it's going to be somewhere around here. So let me draw that point, right? It's going to be right around here somewhere is that inflection point. And at one standard deviation, remember we said that empirical rule tells us that between those 2 points, about 68% of the time, 68.26% of the time will be there. Now, where was Count Buffon's set of 40,040 flips? Where did that take us? Well, that put us right about, not quite one standard deviation, but just inside one standard deviation right there. And so at 0.507, we're not quite up to 0.00787 above. And so we know that that's kind of in that common range. We know the z-score is not 1, it's a little less than 1. The most common thing that practitioners actually do at this point, when they want to finalize the decision, do we want to reject this null hypothesis or not, is to calculate the probability that Count Buffon, with his series of 4,040 flips, what is the probability that he would be farther away than what he actually got? Let me shade in what area I'm describing here when I talk about being further away. It's everything to the right of what he got. Everything on this right tail, and also, here's the thing that you really have to think about, everything on this left side. Let me draw an exactly similar triangle to capture all that area. And just to be picky here, let me tell you that these tails in a normal distribution technically go out forever, so I don't want you to think that we're just doing this triangle region, but everything to the right of 0.507 there. Let's see, 0.507, but we want to get also a similar area. It's going to be the same amount as this area on the left. And so an easy way to do this in this case is just calculate how much area is above 0.507 in this normal distribution and multiply it by 2. How do we do that? Well, we take this z-score 0.889, we look it up on a normal distribution table. I'm going to assume you know how to do that. And normally we have to round these off to 2 decimal places. So if we look this up on a normal distribution table and we round this off to 0.89, kind of rounding it off there, and we look it up on a normal distribution table, we're going to get that there is 0.1867, 18.67% of the time when you flip a coin 4,040 times, you would get actually a higher proportion of heads than Count Buffon got. And because this is a symmetric distribution, you also have another 0.1867 on this side. So the question we're asking here is, what is the probability? What is the total probability? I'll just call that probability for short, that we would get a more extreme sample, a sample further away than 0.507 on the right, or further away, a bigger deviation on the left. What is that probability? Well, we add up the probability it could have been further, more extreme on the right, plus what's the probability it could have been more extreme but on the left, and we add those two together, and we get that total probability is 0.3734. So 0.3734. What does that 0.3734 mean? Well, first we call it a p-value, and exactly what it means is what we just described. Let me put it up top here, and I'll type a little description of what this means. It says that by taking a sample like we did, there is a 37.34% chance that just randomly we could have gotten something further away from the truth when the null hypothesis is true. So there's a 37% chance that a sample could be further away just randomly when the null hypothesis is true. This is an important part of the statement. So when Count Buffon flipped those coins 4,040 times, is his result really weird? Is it really extreme if 37% of the time when people do this, we would expect them to actually be further away? Well, no, that doesn't seem so rare if 36, 37, 38% of the time people are even further away, or our results, we expect them would be further away much of the time. This is not a real weird or rare instance that would make us doubt that this coin that Count Buffon flipped is a fair coin, 50-50. So how big should that probability be before we start to doubt that the null hypothesis is true? Normally, the yardstick that people use is 5%. That if that probability that we would get an answer further away than what we did, if that probability is less than 5%, that means that your answer was kind of weird. It was kind of far away from what the null hypothesis suggests should happen, and so people start rejecting null hypotheses. We call that 5% level alpha, and I highly recommend that you go to the Econometrics 6 Statistical Inference series of lectures and watch the one called Discover Your Inner Alpha, because it's very important that you understand why 5%, why not something else. Now, some people use a 10% chance or a 1% chance, and some people use even less than a 1% chance. It depends on the situation. But basically, to wrap up, because this p-value is bigger than 5%, it's a lot bigger than 5%, it tells us that Count Buffon's result of 50.7% heads is nothing that unusual, given the fact that he flipped a coin 4,040 times. It's about in the range of what we might expect, so we don't reject the null hypothesis in this case. This video has gotten very long, so I'm going to end it here, and then we'll come back and we'll calculate these other two examples of famous coin flippers.